Hello, you are welcome to this class. My name is Dr. Kingsley. In this class, I'll be taking us on factors affecting the rate of chemical reaction. Now, the first factor that affects the rate of chemical reaction that I'll be discussing is increase in pressure. Increase in pressure and decrease in volume, they go the same way. Now, either increase in pressure or decrease in volume. Now, this one applies to gases. Now, we find out that when the pressure of a gas is increased, the volume of the gas will decrease. Now, if we take this lid and we compress it in, we will decrease the volume. So when the volume is decreased, we notice that the number of particles of gas or molecules of gas here is also the number of molecules of gas here. But in this place now, because the volume is decreased, the gas molecules that want to react are more in close proximity with one another, enabling them to collide more. And we know that according to collision theory, the more the frequency of effective collision, the faster the rate of a reaction. So increase in pressure leads to decrease in volume, causing the reacting particles, gas particles, to be in close proximity to collide more with each other. Big volume will lead to less collision, while smaller volume will do will actually lead to more frequency of effective collision. That is why increase in pressure will lead to faster rate of reaction, while decrease in volume, the same thing, will lead to the faster rate of reaction. Then number 2 is nature of the reactant. You look here, this is solid, liquid and gas. We know that the particles of the solid are more compact. They are more compact, which makes movement to be restricted. So the particles of the solid can only vibrate. But the liquid, their molecules are further apart when you compare it to solid. That is why liquid particles, they can undergo both vibrational, rotational and translational motion, allowing the particles to collide more with each other. Now the particles of a gas is very far from one another, thereby motion is random, and collision is also frequent because they move more, so they can collide more with each other. And according to collision theory, the more the number of collision effective, the faster the rate of reaction. So gas particles collide more than liquid, while liquid collide more than solid. That is why the rate of reaction is fastest in gas, followed by liquid, then solid. Now number 3 that we have here is temperature. Number 3 is temperature. Temperature also affects the rate of reaction. Now, if we increase the temperature of a reacting particle, we are increasing the average kinetic energy of that particle. Remember, the average kinetic energy, of a particle of matter is directly proportional to to temperature, which is to say, the more the temperature, the more the kinetic energy. In a real sense, kinetic energy, average kinetic energy, is equals to 3/2 RT. So we can see that average kinetic energy is dependent on temperature, direct proportion. That is why, for example, if we have a gas in a container, at 27 degrees Celsius, this gas molecule will be moving randomly, colliding with one another. However, if we increase to 100 degrees Celsius, you will expect that the particles of this gas will do will be moving faster to collide with one another. Therefore, the frequency of the effective collision will be increased, and therefore leading to to increase in the rate of reaction, because the increase in collision will lead to to faster rate of reaction. Now, it is estimated that that anytime temperature doubles, the rate of reaction also doubles. So temperature affects the rate of reaction. This was explained according to the transition state theory. I mean Arrhenius theory, according to Arrhenius theory, because Arrhenius is saying that the rate constant is equals to A exponent minus EA over RT. You can see that the constant, that is the rate constant, is actually proportional to to temperature, meaning that temperature will always affect the rate of a chemical reaction. Then number 4 that we have today, number 4 is is a surface area. Surface area. The more the surface area of the reacting particles, the faster the rate of reaction. That is why powdered zinc will react faster than zinc granules. Why zinc granules will react faster than lump of zinc? The same thing. Powdered iron will react faster than granules, that is iron filing, and we react faster than the lump of iron. That is to say that when we increase surface area of the reacting particles to be in powder, it will allow more collision to happen. So the more the surface area, the faster the number of collision, and also the speedier the rate of reaction. Now, having taken this, number 5 that affects the rate of reaction, number 5 is catalyst. Now, catalyst affects the rate of reaction. How does catalyst affect the rate of reaction? Catalyst affect the rate of reaction by reducing the activation energy. Now, if we have a reaction coordinate, and here we have energy. Now, this profile we have here, this is the reactant, okay, and this is the product, okay. Here is activated complex, okay. From this point to the place where we have the reactant, from here is the activation energy. So this is activation energy. This is activated complex. Now, if we take the line of the reactant and extrapolate it to this to this place also, from here to here is actually the change in enthalpy of the reaction. Now, what we are saying is if this is uncatalyzed reaction, we can see that the activation energy, let's say here is a 0, here is a 50 joules. Let's take it energy, okay, in joules, and here is 100 joules. Let's say here is 200, and let's say this place is 300 joules. We can see that the activation energy for this reaction will be the energy here, which is the energy at the activated complex, okay, 300 minus the energy of the reactant, which is which is 100. That is to say that the activation energy for this reaction is 200 joules. Now, but if we introduce a catalyst in this reaction, what catalyst does is they bring down the activation energy. Remember, the activation energy is the energy barrier, okay, that is preventing reaction from taking place. So when the energy barrier comes down, then the reaction can proceed faster. Now, if we introduce a constant, okay, you will see that the activation energy, I'm using a broken line to show the catalyzed reaction. This one is the uncatalyzed. Why this is what? They catalyze. Can you see for this one, this is the activated complex. But for the catalyzed reaction, this is the activated what? Complex. So what is the activation energy here? You can see that what? We will be having something from here, okay, to here. Okay, so if we trace this to this place, we might be having something like 280 minus what we have here is what? 100. So the activation energy for the catalyzed reaction now will be around 180, okay, 180 joules. We can now say that what? Catalysts have brought down the what? The activation energy, therefore increasing the rate of what? Of chemical reaction. So these are the factors that affect the rate of chemical reaction. We have a pressure, we have a volume, okay, we have temperature, okay, we have the nature of the reactant, then we have what? Surface area, and we have a catalyst. All these affect the rate of a chemical reaction. Thank you very much. Please do subscribe to my video, okay, share the video, okay, and like the video so that I can get to so many people that need it. Thank you very much. So the seventh factor that affects the rate of reaction is concentration. The more the concentration of the reactant, the more the number of collision, and the faster the rate of reaction. If you look at this, you find out that the reactant here, their molecules are concentrated, so there will be more chance that collision will be more frequent. Why this one? The particles are what? Not concentrated, because we have very few particles, so the chances for collision will be smaller here, and therefore the rate of reaction here will be smaller. So please, as I told you, always subscribe to my video and share them. Thank you.